So now we arrive at the most unsettling idea of all. For over a decade, we believed galactic destiny was simple. Two giants, one outcome, an unavoidable crash written into the fabric of space-time itself. But galaxies don't move through silence. They move through crowded gravity. The Milky Way isn't just falling toward Andromeda, like a stone dropped into a void. It's drifting through a constantly shifting web of invisible forces. Pulls and tugs from nearby galaxies, dark matter filaments, and massive objects we're still struggling to fully map. And that means the future isn't fixed. It's chaotic. Here's an astonishing fact most people never hear. No star in either galaxy is likely to directly collide with another star, even if the galaxies merge. That sounds impossible, right? Two galaxies, trillions of stars, and almost none of them actually hit each other. That's because stars are incredibly far apart. On average, if the sun were the size of a marble, the nearest star would be another marble hundreds of kilometers away. When galaxies pass through one another, it's more like two swarms of gnats drifting through each other in a stadium than two solid objects smashing together. The real violence doesn't happen between stars. It happens between gravity and time. If the Milky Way and Andromeda do intersect, their gravitational fields would stretch and warp both galaxies. Spiral arms would unravel. Entire star systems could be flung into intergalactic space. Some stars would be captured by the opposing galaxy, stolen forever, and our sun, it wouldn't be destroyed, but it could be relocated. Simulations suggest our solar system could be tossed into a long, looping orbit far from the galactic center, or even expelled into the darkness between galaxies, where night would never end and the Milky Way would appear as a glowing ribbon across the sky. But remember, this is no longer guaranteed, because of the Large Magellanic Cloud. Here's another detail that makes this story even stranger. The Large Magellanic Cloud isn't just tugging sideways. It's also sinking into the Milky Way. Astronomers have found that it's surrounded by an enormous halo of dark matter, far larger than anyone expected. That hidden mass amplifies its gravitational influence, meaning its effect on the Milky Way's motion is far greater than its visible stars alone would suggest. In other words, we underestimated it badly. And this is where uncertainty enters the equation in a way astronomers hate. But the universe thrives on. When Sawala's team ran tens of thousands of simulations, slightly tweaking initial conditions each time, the results split cleanly in half. Some futures end in a merger. Some futures end in a near miss. Some show repeated flybys stretching across billions of years, like two cosmic rivals locked in a slow gravitational dance that never quite becomes a collision. The difference between those outcomes? Sometimes just a few kilometers per second in sideways motion. That's it. A rounding error on a cosmic scale. Which means the Milky Way's fate isn't sealed by destiny. It's balanced on precision. And here's the most mind-bending part of all. The universe itself may decide for us. As dark energy continues accelerating cosmic expansion, it subtly changes how galaxy groups evolve. Over unimaginable timescales, even gravity can lose ground. What looks like an inevitable collision today could dissolve into a permanent separation tomorrow. So when people ask, will Andromeda hit the Milky Way? The most honest answer science can now give is this: we don't know. And that uncertainty isn't a failure of astronomy. It's a revelation, because it means our galaxy isn't trapped on rails toward destruction. It's improvising. What Earth's night sky would look like millions of years before impact, and whether intelligent life, if it exists then, would see the warning signs long before the first stars ever cross paths. Stay with me, because the universe hasn't finished rewriting the story yet. And here's where the story goes from spectacular to almost unbelievable. When those two supermassive black holes finally merge, they won't just quietly disappear into the darkness. The collision would release more energy and gravitational waves than all the stars in the observable universe produce in light at that moment. Let that sink in. This wouldn't be an explosion you see. It would be a distortion of space itself. Space would ripple. Time would stretch and compress. If intelligent observers existed anywhere nearby, they wouldn't see the event. They would feel it. As space-time rang like a struck bell, those gravitational waves would travel outward forever, carrying a permanent record of the moment two galaxies truly became one. And the story doesn't end there. The newly formed black hole would likely receive a powerful kick. Depending on how the waves are emitted, the merged black hole could be shoved away from the galactic center at thousands of kilometers per second. In extreme cases, it might even oscillate back and forth through the galaxy, dragging stars with it before eventually settling down. Now zoom out for a moment, because while this drama unfolds at the center, something quieter, but just as important, is happening everywhere else. Star formation begins to fade. During the merger, gas clouds crash together and ignite bursts of new stars. But that fuel doesn't last forever. Once it's used up or blown away, the new galaxy slowly runs out of raw material needed to make stars. The result? A galaxy that grows old. The bright blue stars die first. Then the yellows. Eventually, only long-lived red stars remain, glowing faintly for trillions of years. The galaxy becomes calmer, dimmer, quieter, a cosmic retirement home drifting through an expanding universe. And here's a detail that completely changes how you think about this collision. Even if the Milky Way and Andromeda merge, the local group itself may eventually become isolated because the universe is expanding faster and faster. Distant galaxies are already slipping beyond our cosmic horizon, moving away so quickly that their light will never reach us again. Over enough time, the merged Milky Way Andromeda galaxy could become the only visible galaxy in the sky. Future astronomers, if they exist, might look up and see a universe that appears completely empty. No other galaxies, no evidence of expansion, no clue that a vast cosmos ever existed beyond their own island of stars. Which means this collision isn't just about destruction or survival. It's about what knowledge survives. The Milky Way and Andromeda's dance will shape what future civilizations can know about the universe at all. And now, let's return to the most important twist in this entire story. Because remember, this might never happen. That sideways tug from the Large Magellanic Cloud, the influence of dark matter we can't fully map. Tiny uncertainties in speed and direction. They all add up. The Milky Way might miss Andromeda completely. They could swing past each other, stretch one another with gravity, and then drift apart, scarred, reshaped, but separate. A near miss remembered only in distorted star streams and warped halos. In that future, both galaxies survive, changed but not erased. So what we're really learning here isn't just about galaxies, it's about certainty. For years, we believed the universe ran on fixed tracks, predictable, inevitable, locked in place. But the deeper we look, the more we realize reality is balanced on probabilities. Even events involving trillions of stars can hinge on the smallest forces. And that might be the most humbling lesson of all. The fate of our galaxy isn't written in stone. It's written in motion. And in part 3, we'll explore the biggest unanswered questions of all. Could advanced civilizations survive a galactic near-miss? What signs would warn them millions of years in advance? And what this uncertainty tells us about the ultimate fate of the universe itself. Stay with me, because the universe is far less certain and far more interesting than we were ever told. Right now, detectors like LIGO are incredible at sensing collisions between smaller black holes, the kind formed when massive stars die. But they simply aren't built to hear the deep, slow bass notes produced when supermassive black holes merge. Those signals stretch across space for years, even decades. That's where the future comes in. A space-based observatory called LISA, scheduled for the 2030s, will operate millions of kilometers apart, forming a giant gravitational wave antenna in space. Unlike Earth-based detectors, LISA will be sensitive to the slow, powerful waves produced by galaxy-scale events. If galaxies like ours merge somewhere in the distant universe, LISA should be able to hear it. And when it does, we'll be listening to the same kind of signal our own galaxy's black hole could one day produce. Now let's talk about what happens after those black holes meet. When two supermassive black holes finally combine, the surrounding gas doesn't just fall straight in. It spirals. It heats up. It glows. This process can turn the center of a galaxy into something called an active galactic nucleus, one of the brightest objects in the universe. For a time, that single black hole could outshine every star in its galaxy combined. From a safe distance, it would look like the ignition of a cosmic engine, jets of energy blasting out at near light speed, radiation pouring into space, the very heart of the galaxy blazing. This wouldn't destroy the galaxy, but it would reshape it. And that brings us back to the real lesson of the 2025 research. The headline isn't collision or no collision. The headline is uncertainty. Despite the Hubble Space Telescope, despite Gaia mapping the motion of nearly 2 billion stars, despite running 100,000 simulations on some of the most powerful computers ever built, we still don't know. That's not weakness. That's honesty. On these scales, tiny measurement errors grow over billions of years. A slight uncertainty in mass. A small unknown in velocity. A dark matter halo that extends farther than expected. Over cosmic time, those small differences explode into radically different futures. One path leads to a merger, another to a near miss, another to repeated flybys that stretch both galaxies without ever fusing them. And even the best case scenario isn't calm. If the Milky Way and Andromeda pass within a few 100,000 light years of each other, gravity alone would tear at both galaxies. Star orbits would be scrambled. Long streams of stars would be flung into space. The familiar shape of our galaxy would be permanently altered. The night sky would never look the same again. And yet, here's an astonishing fact. Even in all that chaos, life-ending radiation wouldn't sweep through the galaxy. Planetary systems would mostly remain intact. Stars would survive. The destruction would be architectural, not apocalyptic. Galaxies are fragile in shape, but incredibly durable in substance. Now here's what could change everything. In 2026, Gaia will release a new dataset that improves measurements of Andromeda's sideways motion, the single most important unknown in this entire problem. That update alone could tilt the odds sharply in one direction or the other. At the same time, astronomers are refining maps of dark matter, the invisible scaffolding that holds galaxies together. Dark matter outweighs visible stars by a factor of 5 or more, and its distribution controls how galaxies move far more than their shining matter does. As our picture of that invisible structure improves, so will our predictions. But even then, the universe may refuse to give a final answer. So, let me leave you with 3 takeaways. First, the Andromeda collision is no longer a certainty. What was once described as inevitable is now, at best, a coin flip, and possibly something that never happens within any meaningful timescale. If a merger does occur, it won't be a violent smash of stars. It will be a slow, gravitational reshaping. Individual stars survive. Solar systems mostly endure. The galaxy changes its form, not its existence. Third, and this is the one that matters most, we live at a moment in history where a species on a small planet can simulate the fate of trillions of stars, billions of years into the future, and still be humbled by what it cannot predict. There is something deeply beautiful in that. The Milky Way might continue spinning peacefully for another 10 billion years, forming new stars and new worlds, perhaps watched by civilizations that don't yet exist. Or it may someday merge with Andromeda, becoming something entirely new, older, quieter, and transformed. Right now, science says we don't know which future awaits, but we are watching, we are measuring, we are learning, and that curiosity, that refusal to stop asking, may be the most human thing of all. Make sure you're subscribed with notifications turned on when the next wave of Gaia data arrives. This story will change again, and when it does, I'll be here to tell you what it means for the future of our galaxy Milky Way. Why supermassive black hole mergers are so rare and important. Supermassive black holes don't merge easily. When two galaxies collide, their central black holes don't immediately slam together. First, they orbit each other at huge distances, sometimes thousands of light years apart, trapped in a slow gravitational dance. There's a known problem in astrophysics called the final parsec problem. At about 1 parsec, 3.26 light years apart, black holes can stall. They've already flung away most nearby stars that could help drain their orbital energy. Without something to steal that energy, gas, stars, or another black hole, the merger could take longer than the age of the universe. Why does this matter? Because it means not all galaxy mergers produce a single black hole. Some galaxies may hide binary black holes at their centers for billions of years, quietly orbiting each other. That's one of the mysteries Lisa hopes to solve. 2. What gravitational waves from a galaxy merger really mean. When two supermassive black holes finally merge, the gravitational waves they produce are completely different from those detected by LIGO. Instead of milliseconds-long chirps, these waves, last year's, stretch across millions of kilometers, carry more energy than any other known event except the Big Bang. Here's the wild part. Those waves slightly change the distance between objects everywhere they pass, including atoms. The effect is tiny, but measurable with the right instruments. In theory, a sufficiently advanced civilization could use gravitational waves as a cosmic record, reading the merger history of galaxies across the universe. 3. Why the Large Magellanic Cloud was a game changer. For decades, astronomers thought the Large Magellanic Cloud was just a lightweight satellite. Then Gaia changed that. New measurements revealed it's wrapped in a massive dark matter halo, meaning it's far heavier than it looks. Its gravity isn't a gentle tug. It's a sustained sideways pull on the Milky Way. Important detail. The Large Magellanic Cloud is likely on its first and final pass around the Milky Way. In about 2 billion years, it will merge with our galaxy. That future merger alone will reshape the Milky Way, regardless of what Andromeda does. So even if Andromeda misses us, the Milky Way is still evolving. What dark matter actually does in this story? Dark matter makes up about 85% of the matter in the universe.
Mysterious.
Galaxies are embedded in huge dark matter halos that extend hundreds of thousands of light years beyond visible stars.
Does not shine.
When galaxies approach each other,
glow.
these halos
not
interact
reflect
long before the stars
Yet,
do.
Without
Think of it like two invisible jellyfish colliding before the visible bodies touch. These halos slow galaxies down, redirect trajectories, absorb orbital energy, decide whether galaxies merge or pass by. Without understanding dark matter, predicting the Milky Way's future is like predicting a car crash without knowing where the road is. 5. What the night sky would actually look like. Visual detail. If Andromeda approaches closely, constellations would lose meaning within a few million years. The sky would contain 2 galactic centers. Bright star-forming regions would light up the sky with pink and blue clouds. Long arcs of stars would stretch across the sky like cosmic scars. There would be no impact moment. Just slow, beautiful, terrifying change. Time-lapse the sky over a million years. It would look alive. 6. Could life or civilization survive a merger? This is one of the most surprising answers in astronomy. Yes, easily. Galaxy mergers are too slow to directly threaten life. Radiation increases are localized. Supernova rates rise, but not catastrophically. The biggest risk comes from being too close to the galactic center, being hit by rare gamma ray bursts, long-term changes in star formation. But those risks already exist today. A merger wouldn't wipe out civilizations. It would mostly be a spectacular light show lasting millions of years. 7. The cosmic irony. Future astronomers may never know. Because of dark energy, galaxies beyond a local group are drifting away faster and faster, in tens of billions of years. Only the merged Milky Way Andromeda galaxy may be visible. The cosmic microwave background will fade. Evidence of the Big Bang could disappear. Future scientists might conclude the universe is static and eternal, completely wrong, but with no evidence left to prove otherwise. We are living in a golden age of cosmology, one of the few times in cosmic history when the universe is still readable. 8. Powerful closing line you can use. The Milky Way's future isn't written in stone. It's written in gravity, uncertainty, and time. And for now, the universe isn't done deciding.